Hi, thanks for joining me. Today I've got a fun number theory problem for you. We want to find all positive integers x, y and z such that 2x squared plus 3y squared equals z squared. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so this was in fact sort of a trick question because in fact there are no integer solutions to this guy here. And the way we're going to prove that is by looking at this equation mod some particular number, and what we'll do is we'll show that the left hand side cannot be equal to the right hand side mod that number, and hence they can't be the same in this equation here, so without any modding. But of course we've got to choose some particular number, and that particular number is going to be 8. So we're going to look at this equation mod 8. And the justification for choosing 8, instead of say 9 or 42 or something like that, is, well, we've got a bunch of square numbers, x squared, y squared and z squared, and as we'll see in just a second, when we look at square numbers mod 8, they can only take a few values, which means that our left hand side then will be only limited to a few values, and our right hand side will also only be limited to a few values, so we're only going to have to compare a few values, and of course that kind of has a greater probability of there being inequality, so having none of the values on the left hand side equaling any of the values on the right hand side. But of course, if we look, say, mod some other number, we could get a bunch of different values on this left-hand side and a bunch of different values on the right-hand side, and there is a chance for equality. Anyway, if that doesn't make sense, perhaps once I go through the proof for why there are no solutions to this, it will make a bit more sense. So what we're going to do is first analyze square numbers mod 8. So we're going to take any odd number to start off with. So if you take any odd number, it will be something like 2r plus 1. And then if we square it, well, that's just going to be equal to 4r squared plus 4r plus 1, like so. But notice that this is just 4r times r plus 1 plus 1, like so. But now we have a look at this guy here. Of course, this whole thing is a multiple of 4 because of this 4 here. But then r and r plus 1, well, either r is going to be even, or r plus 1 is going to be even. So if r is even, then r is even, or if r is odd, then r plus 1 will be even. So one of these numbers here will be even, and so when we multiply these two together, we're going to get an even number, and then multiplying it by 4, this thing here is going to be a multiple of 8, so it's going to be 8, say, k, and then of course we've still got this plus 1 out here, so all in all, this is going to be congruent to 1 mod 8, like so, because this thing here is a multiple of 8, and of course we've got our plus 1 here, so this one is just that one there. So if we take any odd number and we square it, it's always going to be congruent to 1 mod 8. Now what if we take an even number? So suppose we have 2r, and then we square that. Well, that of course is just 4r squared, and now of course we've still got our 4 here, but now we've got r squared. So if r is even, then of course r squared will be even, and this will be congruent to 0 mod 8. Okay, but if r is odd, then r squared will also be odd. So this will just be 4 times some odd number. So this will only just be 4 mod 8. It won't be a multiple of 8, but it will be 4 off of a multiple of 8. And of course, every positive integer is either odd or even. So that means any square number, mod 8, can either be 1, and that's if our original number was odd, or it's 0 or 4, so if our original number was even. So all in all, we've shown that any square number you take, it can only take one of three potential values, mod 8, and yeah, so it's either 1, 0 or 4, mod 8. Let me clean up the whiteboard and we'll continue. Okay, so we've just proved that if we take some integer t and then square it, we're either going to get 0, 1 or 4 mod 8. Now, I claim that there are no integer solutions to this guy here, and the way I'm going to prove that is by contradiction. So we're going to suppose for contradiction there's at least one triple xyz which satisfies this equation here. Then what I'm going to do is take a look at the set of all the triples which satisfy this, and take the one which has the smallest z value. So I'm going to choose the one, let's call it, say, x0, y0, z0, where z0 is minimal. Okay, there could be a few with the same z0s, in different x and y's. It doesn't matter, we'll just choose one with the smallest z0, and then what we're going to do is we're going to show that from this we can then go ahead and construct another one with a smaller z value, and of course that contradicts the fact that this z0 is minimal. Now, we have x0, y0 and z0. Well, what do we know from this equation here? Well, our left-hand side is 2 times a square number plus 3 times a square number. So if we go and look at this thing here, 2 times a square number, so this thing here, will be something from the set, or 2 times any of those numbers there. So 0, 2, or 4 times 2 is 8. But of course we're looking at it mod 8, so 8 is just 0 mod 8. So 2x squared is either going to be 0 or 2 mod 8. And this 3y squared guy here, that's going to be 3 times these numbers here. So 3 times 0 is 0, 3 times 1 is 3, and then 3 times 4 is 12, but 12 of course is just 4 mod 8. Like so. So this left hand side and this right, 2x squared plus 3y squared mod 8 is going to be some number from 0 or 2 plus some number from 0, 3 or 4. So all in all, we just have to look at the different combinations. If we do 0 plus 0, that gives us 0. 0 plus 3, that gives us 3. 0 plus 4, that's 4. Then 2 plus 0, that's 2. 2 plus 3, that's 5. And 2 plus 4, that's 6. So let me just bring this 2 here so it's in sequential order. So 2, 3, 4. So all in all, when we do our left hand side and look at it mod 8, it's going to be one of these numbers here. So either 0, 2, 3, 4, 5 or 6. But of course our right hand side is just a square number, so it's either going to be 0, 1 or 4. So this is our left hand side. And then our right hand side therefore is either 0, 1 or 4, because z squared is obviously a square number. So our left hand side has to be in this set here, our right hand side has to be in this set here, but of course our left hand side has to equal our right hand side. So we must choose one of the numbers 0, 1 or 4 from this set here, but of course 1 isn't in this set. So that means that our right hand side must be either 0 or 4 mod 8, because it can't be 1 because 1's not in this set here. So our our right hand side is either 0 or 4 mod 8, and our right hand side of course is z squared. So in particular that means that z squared is even. So that means that z is even. Okay, so from this kind of analysis that we've done, we looked at our left hand side and determined the different possible values it could take, and then we get to this set here. We did the same with the right hand side and we showed that it had to be from one of these numbers here, and of course the left hand side equals the right hand side. So the left hand side and the right hand side, because they're equal mod 8, we've got to have a number which is both in these sets here, and the only two numbers which satisfy that are 0 and 4, but in both cases we get that 0 and 4 mod 8 must imply an even number. So z squared is an even number, so z is even. So that's what we've deduced so far. Let me clean up the whiteboard and we'll continue. Okay, so we've just shown that if we have any solution to our equation here, then z must be even. And of course, because x0, y0 and z0 we're supposing is a solution with minimal z value, in particular we must have that z0 is even. So of course that means we can write z0 equals 2 times z tilde 0, where z tilde 0 is also a positive integer. So this is what we kind of had so far, and what we're going to do is just plug that back into this equation here. Of course we have 2x0 squared plus 3y0 squared equals z0 squared. So just plugging that in, we get 2x0 squared plus 3y0 squared equals, now z0 squared is just 2z tilde 0 squared, like so. And of course if we expand this out, this is just 4z tilde 0 squared, like so. But then of course this guy here is even, this guy here is even, so that must mean 3y0 squared is even, so that means that y0 squared must be even. So in particular y0 then must be even as well. So this implies that y0 is even, so y0 equals 2y tilde 0, like so. And again, we're just going to plug that back into our equation here. So we're going to get 2x0 squared plus now 3y0 squared is just going to be 3 times 4 times y0 tilde squared. And 3 times 4 is of course 12, like so. And that equals 4z tilde 0 squared, like so. So 2x0 squared plus 12y0 tilde squared equals 4z tilde 0 squared, like so. And now the next thing we're going to do is look at both sides mod 4. So up here we looked at, both sides kind of parity, so both sides mod 2. Here we're going to look at it mod 4. Now 12 is a multiple of 4, so this thing here is 0 mod 4. This thing here is also 0 mod 4 because it's a multiple of 4. So we must have that 2x0 squared is a multiple of 4. Now, if x0 was odd, then that means x0 squared would be odd. So that means 2 times x0 squared would only be 2 mod 4 as opposed to 0 mod 4. So we must have that x0 is also even. So that means that x0 must be equal to 2x tilde 0. And you can probably see where we're going with this. We're going to plug that back into our equation. So here we're going to get 2 times 4, which is 8x tilde 0 squared, plus our 12y0 tilde squared equals 4z0 tilde squared, like so. And you guessed it, we're going to now divide this thing here by 4. So the whole equation by 4, it becomes 2x0 tilde squared plus 3y0 tilde squared equals just 1 loss of z0 tilde squared, like so. But in particular, z0 tilde is just z0 over 2. So in particular, it's going to be, we're going to have this equation here holding, oopsie daisy, z0 tilde is less than z0, because they're both positive integers. But remember, we said that x0, y0 and z0 was the solution to this equation here, where z was minimal. And we've just found another one with x0 tilde, y0 tilde and z0 tilde, because of course this guy here is the same as this guy here, except with each of the x, y, z's replaced with the x0 tilde, y0 tilde and z0 tilde. But we have a contradiction because z0 tilde is now strictly less than the z0 we had before. But that's impossible because we said the z0 we had before was the one that corresponded to the minimal solution of this equation here. And so, kind of by an infinite descent argument, if we did have a solution, we could keep finding one smaller and smaller and smaller, and that's impossible because x, y, and z are bounded below by 1 each. They each have to be at least 1. Anyway, that concludes our proof, and hence there cannot be any positive integer solutions to this guy here. I hope that has all made sense. Thank you for watching. I'll catch you in the next one. Have a great day.